Hi, everyone. Thank you once again for tuning into the lecture earlier today. And I hope this lab reinforces some of the ideas that were introduced to you in the lecture. So in particular, we're going to focus on these hardware efficient family of trial states for variational quantum eigensolvers and try and work through some of the building blocks, if I may, for using this in a variational quantum eigensolver for solving a simple fermionic Hamiltonian, okay, for solving the ground state for simple fermionic Hamiltonian. In particular, we're going to use the example of hydrogen, and this was something I spoke about in my lecture as well, where these terms represent it's a tensor products of these Pauli matrices acting on the first qubit and acting on the second qubit. Okay. So for this Hamiltonian, we're going to try and construct a guess state, and that hardware efficient trial state. The first guess is defined in this block. We're going to define this for a depth 2 circuit with using C0 gates as the entangler steps. And then I spoke about how one could use parameterized single qubit rotations, right, as the parameters for the trial. So that's what we're going to do. We're going to use a specific form of RY RZ, which means a Y rotation followed by a Z rotation. So the initial set of angles are parameterized by angle 1, and then as we begin to interleave the entanglers with additional single qubit rotations, they're parameterized by angle 2. For the first guess, we're going to start out with all of these set to pi over 2, and that's what that circuit looks like. You can see you have these two entangling blocks or entanglers with C naughts, and then they're sandwiched by RY RZs on both qubits. And for the first guess in the optimization, we're going to set all of these angles to pi over 2. Okay, and then the lab walks you through how you would measure the ZZ expectation value. This is something I detailed in my lab, in my lecture, and took you guys through. I will emphasize making sure that you understand how the ZZ expectation is constructed from the counts. This is also something I described in the lecture. And specifically then going on to additional terms in the Hamiltonian, the ZI and the IZ, convincing yourself that we don't need additional circuits for the measurement of these terms. One could, in principle, use just these counts, right? So convincing yourself how ZI and IZ here are measured. That is also an important takeaway message. Okay, and then the remaining expectation is basically XX, right? So here, this is your first graded section where you're required to write down the circuit that would need to be run to measure the XX expectation value. Once you have that, once again, it's important to understand how you measure that from the counts for the circuit that you ran here. And then once you have all the different expectation values of the different Pauli strings in the Hamiltonian, you can join all of that together and get an estimate of the energy. Okay, I'll remind you all that these coefficients are all functions of the interatomic distance. So this represents the Hamiltonian at a particular interatomic spacing. Okay. Okay. Now I want to give you a sense of how gradient descent works, specifically for the example of SPSA, which was the optimization that we discussed in the lecture, where we can approximate the gradient using just 2 measurements. Okay, so in this example, if I scroll back up again, we're going to keep all of these angles fixed, the angle 2s, and just change angle 1. Okay, around this angle 1 value of pi 2, we're going to go, just give me one second. We're going to go plus 0.1 pi over 2, and we're going to go minus 0.1 pi over 2 for all the angle ones, okay? And we're going to remeasure the energies at these points. And from a measurement of these energies, I want you to get a sense of in which direction you would go for the next optimization step. So that's going to involve getting an estimate of the gradient, okay? A lot of these functions are perhaps already accessible through Qiskit Aqua for more complex problems. But for a first attempt, I think it's very beneficial to actually walk through how these simple building blocks actually work together. And I think running through this will give you some intuition for that. Okay. In all of these problems, the number of shots is very large. In the next step, I'd like you to run these for different sets of shots. This is a bonus problem for 100 and for 1,000 or 10,000 shots, and see how shot noise is going to affect your gradient estimation and how it's going to affect decisions that you might have to make regarding, decisions the classical optimizer would need to make regarding which direction to go in for the next iteration. Okay, this is also an important step to appreciate how the number of shots is a very important aspect of the success of a VQE. Okay, and the final bonus question is, well, given that Hamiltonian, can you find out what the exact ground state energy is? And the way you would do that is you express the Hamiltonian. You have a matrix representation of the Hamiltonian, expressing it in terms of the different Pauli matrices. Once you have that matrix, you diagonalize it and find its energy eigenvalues. And the lowest one is the ground state. Okay, so that's what you need to do. I hope you've enjoyed your introduction to trying to do chemistry with quantum computers. Thank you for your interest, and good luck with the lab. Thanks.